Okay. Am I audible now? Hello? Am I audible?
Yes, sir.
Yes, yes, sir.
Okay, fine. So, I will, 1 minute, I will put it per presentation. Okay, we'll start with the photosensitization. So, photosensitization means, as you are aware that a carbonyl compounds, direct irradiation, it will go to the triplet stage via singlet one. Whereas the olefins does not go to the triplet state because uh, triplet state, excited state products are different from the singlet state uh, excited molecules are different. So that's the reason it is possible to make or convert the olefins to the triplet state with the help of the photosensitizer. So photosensitizer means these will act as a energy donor. It means that photosensitizer donor, we can call it as a donor also. Donor is the source of energy said to be triplet photosensitizer. That means let us consider that benzophenone is a photosensitizer. Then what will happen? It is irradiated. It will go to the initial stage singlet one, and later on it will go to the triplet state. Okay, so that is in the case of donor one. So here, what is acceptor? Acceptor means usually in this case olefins, and the acceptors take the energy from the donor, and the acceptor directly go to the triplet state. And donor, we will call it as a photosensitizers. Acceptor, we will call it as a quencher. Okay, triplet quenchers. This is about the concept of photosensitization. So what you can remember, most of the organic compounds on irradiation, they will go to the singlet state. But few of the organic compounds, they won't go to the triplet state. For example, olefins. In order to make olefins to the triplet state, it is possible to use in the reaction media a photosensitizers. For example, carbonyl compounds are the example. So carbonyl compounds can act as a photosensitizers. It means that on irradiation of carbonyl compounds, they will go to the initially singlet, and then later they will go to the triplet stage. Once they reach the triplet stage, they can donate the energy to the substrate. If the substrate is olefin, if energy it is taking from the carbonyl triplet state energy, then olefins directly enters to the triplet state. In this process, carbonyl compounds acts as a donor, and they are called as photosensitizers, triplet photosensitizers. And olefins called as an acceptor, and they are energy gainer, and they also called as a triplet quencher. Is it clear? Any question? If there are no question, these words, I will take it in terms of equations. So here I'm taking an equation. A0 means ground state acceptor. D0 means ground state donor. So on irradiation, donor will go to the singlet state. This is the singlet state. And then donor one crosses the intersystem crossing. So on intersystem crossing only, singlet will be converted into triplet. Again, the triplet formed is the donor one. At this stage, triplet form of the donor react with the acceptor olefin. It means that it transfers the energy from donor to the acceptor. Then acceptor directly enters to the triplet state, directly enter to the triplet state. This is a complete, this process is called as photosensitization. Any questions? If there are no questions, I will go to the next slide. Anyway, I will repeat once again. Acceptor A0 means acceptor ground state. D0 means donor ground state. On irradiation with light, more particularly, a donor maximum wavelength is used for the irradiation. Then donor gets converted into singlet. Then this singlet crosses the intersystem crossing and converted into triplet. And then triplet one gives energy to the ground state acceptor, and triplet, after giving the energy, it comes to the ground state, and after gaining energy, acceptor is converted into triplet. This process is called photosensitization. I will go to the next slide. So here, a few limitations are there for the photosensitization. So what are the limitations? You can also call it as a conditions. Then here, what is the condition? Energy of the triplet of a donor should be greater than the energy of the triplet of the acceptor. That is one condition. Another condition is energy of the triplet of a donor is less than the energy of the singlet of acceptor. These two are the conditions. Then for the better photosensitization, concentration of donor must be greater than the concentration of acceptor for efficient photosensitization. So these two conditions you can mention it for the limitations of photosensitization. Here is the diagram. In this diagram, a carbonyl compound called benzophenone is the donor, butadiene is the acceptor, and it's a triplet quencher. Another name for the acceptor is a triplet quencher. Another name for the donor is the triplet sensitizer. And this is the ground state one, means ground state means ground state molecule. This is also a ground state molecule of butadiene, ground state molecule of benzophenone. And this will be the triplet state of the butadiene, and this will be the triplet state of the benzophenone. You can also observe that triplet state of the benzophenone is higher energy compared to the triplet state of the acceptor. This is, with this, I can go to the next slide. In the next slide, I'm taking few examples. The first example is the benzophenone. This is the one. So benzophenone means two phenyl groups are attached to the carbonyl carbon is called benzophenone. So this is again, it is in the ground state, and it can, of course, the acceptor butadiene is also in ground state. When it is irradiated, the carbonyl compound gets converted into singlet stage, whereas the butadiene, it is in the ground state. Then a carbonyl compounds crosses the intersystem crossing and converted into triplet one. Now the triplet, it is donates the energy to the ground state of the butadiene. Now butadiene is converted into triplet, and triplet benzophenone is converted into ground state because it donates energy to the acceptor. So in this process, benzophenone is the photosensitizer and butadiene is the acceptor. This is one example. I will go to the next slide. So here I'm comparison of the ground state and excited state. geometry, more particularly geometry of the excited state may differ from the ground state. So you can observe that there are two kinds. This is again alkyne. This on irradiation, two kinds of irradiation. One is vertical transition and non-vertical transition. In the non-vertical transition, geometry of the ground state and the excited states are different. Whereas in the vertical transitions, geometry of the ground state and the excited states are same. And here one more example we are taking. What is that example? Is carbonyl compound, more particularly formaldehyde. And you can observe that it's a trigonal planar one. So trigonal planar one on irradiation with light, it's converted into excited state. Excited state slowly turn to the pyramidal shape. So pyramidal shape and trigonal shape, there is a geometrical changes. And you can also observe that dipole moment of the trigonal formaldehyde is different from the dipole moment of the pyramidal formaldehyde. I will go to the next slide. In the next slide, you can observe that the advantages of the molecule are organic molecule on irradiation, the properties, chemical properties changes. What is that chemical properties? The excited molecule can act as an oxidizing reducing agent. That means it can gain electron or it ready to lose electron. That means excited state molecule can act as a strong in losing or gaining electron. That means redox property. Redox property means oxidation reduction property. Excited states stronger redox agents than the ground state. So that means excited state molecules are the better or best strong reducing agents compared to the ground state of the molecule. Here we are showing that this is the energy level 1, energy ground state energy electronic transitions, and these are vibrational changes. And when it is moving, when the molecule is irradiated with light, you can observe that this is again electronic transitions at 0 stage or ground state, and this is the E1, energy level 1. Okay, and that means the molecule is moving from after taking energy from the light source, the electrons will move towards the E1 one. E1 means energy level 1 or electron transition 1 level. This is again a ground state 1, ground state electronic transitions, and energy level 1 electronic transitions. These two are like that. So with this, I will go to the next slide. So here I am taking the few examples. A ground state butadiene react with the excited state of the butadiene. So that means it will undergo. Okay, 1 minute. You know that here what is the symbol used? Symbol used the thermal one. Thermal one means it is not a photochemical reaction. It is a thermal reaction, and in the thermal reaction, cyclization is possible. Correct, now? More particularly, electrocyclic reactions. But at the same time, if it is one of the 4+2 cycloadditions, that means reacting of the butadiene and plus one of the double bond of the butadiene react with the diene, then this product will be the product. More particularly, endo product will be the major product with respect to thermal reaction, because there is a thermal symbol is there. So here, photochemical reactions, and you know that conrotation, disrotation. Disrotation will be the favorable one and forming a product. And you can also observe that the products are different if there is a singlet state or the triplet state. So here the reactants are same. What are the reactants? Butadiene is the reactant, and the ground state. Butadiene is the reactant and the ground state. But butadiene on direct irradiation. So direct irradiation means it can only form the singlet state, but cannot pass the intersystem crossing. That means there is no triplet formation in the direct irradiation. So then what will happen? These pi electron can undergo homolytic cleavage and can form a bond between this carbon and this carbon, this carbon and this carbon. So that is how a bicyclic compound is obtained. Similarly, other possibility is electrocyclization, forming a cyclobutadiene. Only 10% is the dimer is formed. So dimer means there are two different dimerization possibilities. And then when it comes to the butadiene irradiation with the triplet sensitizer. The triplet sensitizer may be a benzophenol. In such case, a triplet excited state is obtained, and the triplet excited state can lead to a formation of dimer product. This is one dimer, this is another dimer. What's the difference between these two? You can observe that here cis trans. Okay, so this one will be the cis one. This one will be the. This is that cis one. This is the trans one. Okay, trans vinyl cyclobutadiene, cis vinyl cyclobutadiene, and this is also a adduct formed one. Adducted means 4+2 cycloaddition one. Right. Overall, you can observe that singlet transition state 1 gives rise to cyclization product with the 10% dimerized product, whereas in the triplet transition state 1 gives you majorly the dimer product. With this, I will go to the next slide. So here I am taking the photochemistry of carbonyl compounds. Simple photo additions are one kind of photochemistry of carbonyl compounds we are discussing. Another kind is photocycloadditions, and then one more is photocleavage, and one more is photorearrangement. Photo additions. So it's one kind of photochemical reactions of carbonyl compound. Photocycloadditions is another kind of photochemistry of carbonyl compound. Photocleavage is another kind of photochemistry of carbonyl compound. Photorearrangement is another kind of photochemistry of carbonyl compounds. Let's take the first one, photo reductions. So photo reductions means proto reduction similar to the reduction of carbonyl compound. So here in general terminology, CC indicates that carbonyl compound. Here a hydrogen donor is used. And the carbonyl compounds are irradiated at the lambda max, means maximum absorption of the carbonyl compound. What are the products obtained? The products obtained are simple alcohols. That means a secondary ketone is converted into secondary alcohol. So in addition to the alcohol, it is also observed that pinacols. Pinacol means 1,2-diol. 1,2-diol containing compounds are called pinacols. In addition to the alcohols, pinacols, there is another side products also formed in the photo reductions. So here I am taking an example. This is a carbonyl compound, more particularly benzophenone, and this one is the hydrogen donor. Hydrogen donor means it's a solvent, more particularly an alcohol, and it's an isopropanol. And these compounds having the weak CH function. That means this CH function is weak. Example, alcohols, amides, or can be used as a hydrogen donor. So when these two are irradiated, more particularly the wavelength of the carbonyl compound, lambda max wavelength of the carbonyl compound, forming a benzhydral. Name of this compound is benzhydral, BENZHYDRAL. HYDROL, bench-hydral. So conversion of benzophenone to bench-hydral. In addition to that, a pinnacle is formed. Name of the pinnacle is called benz-pinnacle. I think this you are going to prepare in the same method. What is that same method? Irradiation of benzophenone, pinnacle-pinnacolone rearrangement. Here there is an involvement of rearrangement called pinnacle-pinnacolone rearrangement. So pinnacle is obtained. I think there is an experiment in the practical. You have to take the benzophenone and isopropanol. Uh, you can use a initiator, radical initiator. Otherwise, you can just keep these are irradiated with the light, sunlight or UV visible light. So obtained after a few days or 1 week, you will get a crystals. Both are liquid. In place of liquid, you will get a crystal. The crystal is called bench pinnacle. So in addition to the formation of bench pinnacle, the hydrogen donor is converted into ketone. And one more possibility in the mechanism, it is possible to get a dimerized product between the hydrogen donor and the carbonyl compound, that is this one. Otherwise, here there is a radical formation. That radical undergoes dimerization. That is this product. So overall, many products are forming. Out of many, one will be the major. That is bench pinnacolone, means 1,2-diol formation will be the major one. I will go to the next slide. So what are the characteristics of the photoreductions? A reaction mixture irradiated at the absorption wavelength of the carbonyl compound. That is one characteristics of the photoreductions. Then reaction excited states are N to pi star. I think you know that carbonyl compounds means two kinds of transition, that is pi to pi star and N to pi star transitions. Pi to pi star transitions are called as allowed transitions, and these are called as forbidden transitions. Here the forbidden transitions means slow reaction, not the fast one. Okay. And excitation wavelength can be known by UV visible spectra. Then all the time reduction of carbonyl compounds at excited state. Hydrogen donor at the ground state. What it means? The carbonyl compounds are at the excited state and hydrogen donor, that means alcohol. In this case, benzophenone will be in the excited state. The alcohol, isopropanol, hydrogen donor at the ground state. Are the compounds having weak, means hydrogen donor should be having weak CH group. For example, what are the hydrogen donors? Alcohols are the hydrogen donors, amines are the hydrogen donors, amides are the alkali hydrogen donors, allylic compounds or benzylic compounds are the hydrogen donors, cycloalkanes are the metal hydrides can also act as a hydrogen donor, tertiary butyl weak CH bond, okay, containing one can act as a hydrogen donors. Then usually the reaction intermediate, that means photoreduction, the intermediates are the radical one. The carbonyl compounds having the triplet configuration, that means pi to pi star triplet reductions are highly difficult. Special conditions are required for carbonyl compounds, photoreduction compounds. Then reaction product. What are the products of the photoreduction? Alcohols are the products, pinnacles are the products, and the disproportionate products. What are the disproportionate products? Mixed pinnacles are the mixed and self condensed one are the disproportionate product. Then what is disproportionate products? Reaction which proceeds oxidation as well as reduction products are called disproportionate reactions. With this, I will go to the next slide. So here I am taking an example, photo reduction mechanism. So, what is the mechanism involved in the photo reduction? Here I am taking a benzophenone. So benzophenone react with the isopropanol on lambda max of on irradiation of the lambda max of the carbonyl compound. Carbonyl compound means benzophenone. So what are the products you will get? You will get benzhydral is the one product. Phenol is another product. Acetone. This is how acetone is formed. Isopropanol is converted into acetone. Mixed phenols. What are the mixed phenols? These are the mixed phenols. Then, if we are looking at the mechanism, so this is again a reaction. These two are reactants. A light source is responsible for the product formation. Benzhydral, one product, phenol, another product, acetone, one more product, and mixed phenols. So mixed phenol means these are the mixed phenols. Then, if we are looking at the mechanism, a ground state carbonyl benzophenone converted on irradiation, converted into singlet benzophenone converted into triplet. So from here to here, it's called intersystem crossing, forming a triplet one. So this triplet benzophenone obstructs the proton from the hydrogen donor. This is the hydrogen donor. So then what will happen? If the hydrogen donor means it only takes the hydrogen radical. So the byproduct formed one with the isopropyl radical. Then here two products are obtained. One is benzhydral radical, isopropanol radical. These two can combine, form this phenol, and isopropanol radical and isopropanol radical can combine, form a dimerizing product. And then benzhydral radical can obstruct the hydrogen radical from the one more source of the hydrogen one. Then benzhydral will be the product. And suppose the benzhydral radical, if it undergoes dimerization, it will form a phenol one. Okay, so that means I'm having another 10 minutes. If you have any questions, you can ask me. Otherwise, I will keep going. So this is a overall. You can remember that this is the reaction. A benzophenone is converted into benzhydral, phenol, and acetone, and also mixed phenols. And this is again mechanism. In this mechanism, one thing is common. What is that common? Carbonyl compounds are irradiated with light with the wavelength of the lambda max of the carbonyl compound. Initially, singlet is formed. Later on, triplet singlet crosses the intersystem crossing and form a triplet. Triplet obstructs the hydrogen radical and forms a radical intermediates. These radical intermediate combine to form a different products. Out of this product, bench-phenol will be the major product. Remaining are minor product. So I will go to the one more example, one more thing concept. What is that one more concept? Or suppose aromatic carbonyl compounds having the ortho-CH function. Look here, this is an benzophenone. Suppose benzophenone is having a alpha CH group. This is a alpha CH group. Then such compounds does not undergo photoreduction. Then these type of molecules undergo photoenolization. So I will tell you what is enolization. Enol formation. Enol formation means formation of double bond here and then conversion of carbonyl compound into OH. That's called enol formation. What it means? A carbonyl compounds having alpha hydrogen. This is the alpha hydrogen. Is it alpha hydrogen? No. What we can say that aromatic compounds having substitution at the alpha position, more particularly the alpha hydrogen aromatic compounds, aromatic carbonyl compound does not undergo photoreduction. Instead of, they will go for photoenolization. And here, this is also a alpha hydrogen is there. Aromatic alpha substitution having alpha hydrogen. So such compound does not undergo photo reduction, but instead of that, they will go photoenolization. Here you can observe that there is no hydrogen at the ortho position. Here also there is no hydrogen at the alpha position. These kind of molecules undergo photoreduction. What is photoreduction? The reduction of carbonyl compound converted into alcohol or are the products. I will go to the next slide. So here, reaction. What is the reaction? Photoenol. So how the photoenol is formed? So that means one of the hydrogen means undergoes homolytic cleavage, and pi bond undergoes homolytic cleavage, forming a double bond here, forming a double bond here, forming a single bond here. That is how photoenol is obtained. What it means? It means that all ortho substituted aromatic carbonyl compounds undergo photoenolization, not the photo reduction. So here is the mechanism how a ortho substituted hydrogen containing carbonyl compound undergo photoenolization, photoenol formation. Okay, I will go to the next slide. So here, evidence for the photoenol formation. What is the evidence? Formed enol can be trapped using dienophile. This is the dienophile. Then what will be the product? 4 plus 2 cycloaddition product. And this is the product obtained. Similarly, a dienophile can be changed. Okay, this is the reactant of the enol, and this is the dienophile. So between here, three examples, and all the three examples having different dienophile, but diene is different. What is diene here? Photoenol is the diene, and the products all are adducts. Adducts means 4 plus 2 cycloaddition adduct, and at the same time, you know that in all these case, endo will be the major product because it's a 4 plus 2 cycloaddition. What is endo? These groups should be towards the newly formed diene. This way, here between these two carbon, newly formed diene. So where is that diene? This is the one will be the diene. That means these groups are towards inside the moiety. Okay. This is about the evidence. What is that evidence? 4 plus 2 cycloaddition adduct endo product formation will be the evidence. That means photoenol enol can be trapped using dienophile. If the adduct formation, this indicates that photoenolization is possible. Right. Then evidence for the reversible formation of photoenol. So you know that photoenols, ketoenol, this is nothing but a ketoenol tautomerism. So photoenol can be converted into ketone. So for that evidence, suppose photoenolization carried out in presence of deuterated methanol. In such case, what will happen? The ortho substituted hydrogen will be replaced with the deuteronium. So if the alpha deuterated substituted product is formed, this indicates that photoenolization evidence. So here I am taking both are, this is a benzophenol, orthomethyl benzophenol, and this is also a orthomethyl benzophenol. This is again a different one, benzyl benzophenol. So this group is called orthobenzyl benzophenol. This is also a orthobenzyl benzophenol. So all these things, if you are irradiating in presence of a deuterated methanol, the ortho substituted proton will be replaced with the deuteronium. So deuteronium is a heavy one. It will replace the hydrogen via photoenol tautomerism. Is it clear? So overall, you can say that incorporation of the D from the solvent medium clearly evidence for the reversible formation of photoenol. So with this, I will go to the next slide. So here, three means there is no hydrogen, but there is a deuterium. So this also means orthodeuterated methyl benzophenone also undergoes photoenol tautomerism. This is the photoenol tautomerism. And suppose in play ortho, if there is a group, what is that group? Tertiary butyl group, other than hydrogen at the ortho position. In such case, there is no photoenol formation, but there is a photoreduction. What is photoreduction? Conversion of this ketone into alcohol. And one more photoreducted product is pinnacle product. This is the pinnacle product means 1,2-diol. 1,2-diol is the pinnacle product. In addition to this 1,2-pinnacle, there is a mixed pinnacle also possible. What are the mixed pinnacle? One benzophenone 1 and one more is isopropanol. That will be the mixed one. Self-condensation. This is the self one. And yes, and one more will be isopropanol radical itself combined and forms a pinnacle. That will be the one more one. So in place of at ortho position, if there is a trichlorocarbon, in such case, this is also undergo photoreduction, not the photoenol. So that means photoreduction means conversion of carbonyl compound into alcohol and pinnacle formation. So with this, I will go to the next slide. So here, benzophenone having strong electron donating group, such as NH2, OH group at the ortho and para positions. In such case, photoreduction depends on the solvents. Now, what are the solvents?